Hello dear students, today I will discuss about some properties of eigenvalues and eigenvectors. We know eigenvalues of a matrix can be found by using characteristic equation of the matrix, a square matrix. We are discussing about matrices as a square matrix. Okay, so here properties of eigenvalues. So there are many properties of eigenvalues and eigenvectors also, and we have to try to find eigenvalues and eigenvectors of a matrix by using properties or by using characteristic equations and simultaneous homogeneous equations. Okay, so just we know transpose, inverse of a matrix. So here first property, see first property, that is what? The eigenvalues, a square matrix A and its transpose have same eigenvalues. Means suppose first property here, let A be a square matrix. Square matrix. Okay, let A be a square matrix of order n. Let A be a square matrix of order n, means n row square matrix. Okay, then as we know that eigenvalues are given by characteristic equation, and we know characteristic equation is what? Then we have A minus lambda I. We know what? A minus lambda I. A minus lambda I. Determinant is equals to 0. This is matrix. Minus lambda scalars. I is unit matrix of same order as A. So this is equals to 0. This is characteristic equation. By solving this is polynomial in lambda. Solving this, we can get the value of lambda, that are the eigenvalues. So here this gives roots eigenvalues of matrix A. Now we are having, suppose this is what? A matrix. A is a matrix and I is also a matrix. Lambda is also matrix. Subtraction is also a matrix. This is a single matrix. Now its dash complement is equals to A dash minus lambda I dash. This is equals to what? A dash minus lambda I dash equals to A dash minus lambda I. So we get it like this. Okay. Now our target is what? Eigenvalues of A and A dash are same. Okay. So here this equals to this. Here by property of transpose we know this is equals to this by using properties of transpose. So a dash, this is dash equals to this. Now we can write a minus lambda I dash determinant equals to a dash minus lambda I. Taking determinants on both sides. Matrix. So here we can write a minus lambda I equals to a dash minus lambda I, because this dash determinant is equals to single this determinant. Since a dash determinant, or we can write for other matrix, suppose determinant b dash equals to determinant b. This determinant of b dash equals to determinant b, means transpose and itself matrix determinant are equal, so we can write like this. Now here characteristic equation of a is this equals to 0, characteristic equation of a dash is this is equals to 0. So from here we can say that if lambda is eigenvalue of this equals to 0, a root of this equals to 0, lambda is also a root of this equals to 0. Okay, so we can write how, because eigenvalues are getting from characteristic equation. So here a minus lambda I determinant is equals to 0 if and only if determinant a dash minus lambda I is equals to 0. Means if this is equal to 0, then this is equal to 0. If this is equals to 0, if and only if this is equals to 0. If this is equals to 0, so its root eigenvalue. Same, its root eigenvalue. Both are lambda. So implies lambda is eigenvalue of A if and only if here lambda is eigenvalue of A dash. Clear? Implies eigenvalues of A and A dash are same. This is first property. A and its transpose having same eigenvalue. Eigenvalues of A and A dash are same. Okay. Second, eigenvalues of a triangular matrix are the just element of principal diagonal elements. Okay. Triangular matrix means just we can write upper triangular matrix, lower triangular matrix. Triangular matrix means one side of principal diagonal elements are 0. Okay. So property 2, what? Principal eigenvalues of triangular matrix are principal diagonal elements. Clear? So here see. Second, let A be a triangular matrix. Okay. So let triangular matrix means just write triangular matrix like this: A1 1, A1 2, A1 n, 0, A22, A2n, 0 0, A33, A3n, 0 0 0, ANN. Like this. One side the element are 0. This side are 0, so triangular matrix. So let A equal to this be n by n triangular matrix, upper triangular matrix. Okay. Just we have to show that its eigenvalues are A11, A12, A33, A44 and AN. These diagonal elements. Okay. Here eigenvalues are roots of characteristic equation, that is A minus lambda I determinant equals to 0. Its roots are, eigenvalues are roots of this. So here we see that A minus lambda I here. So diagonal elements A11 minus lambda, A22, A12, A1n, similarly 0, A22 minus lambda, A2n, and so on, 0, 0, and so on, n minus lambda. This minus lambda I, that means the diagonal elements are subtracted by lambda. This is equals to 0. Now after solving this, we can get what? A11 minus lambda, A22 minus lambda, and so on, ANN minus lambda. So this is characteristic equation, and it gives what? Lambda is equals to A11, A12, A1n, NN. That means what? Principal diagonal elements. Because this gives what? This. After solving this determinant, we can get like this. So A lambda equal to A11, A12, A1, NN. These are the eigenvalues. So eigenvalues are principal diagonal elements. These elements implies eigenvalues of A are principal diagonal elements. Okay, so principal diagonal elements. Now this is the second property, triangular matrix having principal diagonal elements as a eigenvalues. Third property, eigenvalues of a diagonal matrix are the diagonal elements of the matrix. So diagonal, it is very simple. It can be also proved by, just see it. Third property, diagonal element matrix can be taken as like this. They are all 0. Only diagonal elements are there. And so on. This is diagonal. diagonal. So let A equal to diagonal matrix. Then also you can get like this. Its solution is also this. So eigenvalues of A are diagonal elements. Diagonal elements. This is the third property. Same as upper triangular matrix or lower triangular matrix or diagonal matrix. Eigenvalues are diagonal elements only. Okay. Now fourth property. Eigenvalue of an idempotent matrix are either 0 or 1. Idempotent matrix means idempotent rule will follow for that matrix. The fourth property is what? Idempotent means A square equals to A. If A is a square matrix, then A square equals to A for idempotent matrix. So we can prove it that if A is idempotent matrix, then its eigenvalues are either 0 or 1. How? See property 4. Okay, property 4. Eigenvalues of idempotent matrix are either 0 or 1. How? We know when we consider Ax equals to lambda x, this is linear transformation. From this transformation we are getting a value what? A minus lambda I x is equals to 0 matrix. This is homogeneous system of equation. This is coefficient matrix. This determinant is equal to 0 for non-zero solution. Non-zero solution gives the value of x, that is eigen vector. That is eigen vector. And for getting non-zero solution for a particular value of lambda, determinant of this A minus lambda I is equals to 0. So this is characteristic equation of the matrix A. Okay, of this transformation. From solving this, we get eigenvalues corresponding to each value. This system will give its non-zero solution, that is x, as a vector called eigenvector. So here, if there is a eigenvalue of a matrix A, then there is a eigenvector corresponding to this lambda. Okay, so here just we have to prove that if A is an idempotent matrix, then its diagonal eigenvalues are either 0 or 1. So here let A be matrix. Okay, idempotent. Clear? Then we know what? A square equals to A. This is the idempotent rule. Okay. Now, just suppose lambda is eigenvalue of A. If lambda is eigenvalue of A, then there exists a vector x such that Ax equals to lambda x. This is our rule. Lambda is eigenvalue of this. Then there exists a vector corresponding to this lambda such that Ax equals to lambda x. Okay. Now pre-multiply, because we are proving lambda equals to either 0 or 1. So here just pre-multiply this by A. So pre-multiplying by A. So we can get by associativity this equals to lambda A x. Clear? Now here we see that A square equals to A, Ax equals to lambda x. So Ax equals to lambda x implies Ax equals to lambda square x. Now we are using here what? A square equals to A, this, and here Ax equal to lambda x. This is 1, this is 2. Using 1 and 2. Clear? Now, here see, Ax equal to lambda square x. Ax equal to lambda x. So this is third. From second and third, we get second and third. That means this and this. X. So lambda x equal to lambda square x. Lambda x equals to lambda square x. Here, just transferring, we can get lambda minus lambda square x equals to 0. X, there exists non-zero vector. There exists, we can write non-zero vector. Non-zero vectors. Well, non-zero solution will exist. So non-zero vector. So this is non-zero vector. Therefore, this is equals to 0. Okay. So implies lambda square minus lambda x equals to 0 also. Lambda square minus lambda equals to 0 since x is non-zero. Implies what? Lambda minus 1 equals to 0 implies lambda equals to 1, 0 or 1. And lambda is what? Eigenvalue of idempotent matrix. Thus, eigenvalues of idempotent matrix are either 0 or 1. Either 0 or 1. This is the fourth property. Now fifth, the sum of eigenvalues of a matrix is the trace of the matrix. Trace means sum of the elements in principal diagonal of a matrix. Because if we are having a square matrix, then principal diagonal is there. The sum of all the elements of principal diagonal is known as trace of the matrix. So sum of eigenvalues of a matrix is equals to the sum of elements in the principal diagonal, that is trace. Okay, this is the fifth property. So very important property. By using this property we can find solution of different type of questions. Whenever the sum of eigenvalues and product of eigenvalues is also there. Another property, here sum, fifth property. Okay, so this property can be solved easily for two second order matrix and third order matrix, fourth order also. We can extend this. So here take only for third order matrix. Okay. So fifth property. Fifth. Let A, matrix A is equals to third order matrix. Consider third order matrix. Okay. So here let's A11, A12, A13, 21, 22, 23, 31, 332 and 33. This is 3 by 3 matrix. Suppose for 3 by 3 matrix we have to prove this property. What? Sum of eigenvalues is equals to the sum of elements on principal diagonal. That is sum of A11 plus A22 plus A33. Then eigenvalues are given by what? A minus lambda I, determinant equals to 0. Okay, so we can solve it. So A11 minus lambda, A22 minus lambda, A33 minus lambda, and remaining elements are same. 21, 12, 13, A23, A31, A32. So this is equals to 0. Solving. By solving this, we can get, just see, expand this determinant. So by solving this, we can get cubic equation in lambda, because lambda here, lambda here, lambda here, all on minus sign 3 times. So minus lambda power 3, highest power of lambda. So minus lambda power 3, highest power of lambda. And then lambda square term will be there. Lambda square term will be there. When this into this lambda square, this lambda square is multiplied to here. So A33 will be the coefficient of lambda square. So we can see here lambda square A11, A12, A22, A33, then minus lambda cube, lambda square, lambda, and finally constant term equals to 0. This type of equation we are getting. Okay, so eigenvalues are given by this. Clear? Just consider on the this part, characteristic polynomial, 0 of this polynomial. This characteristic polynomial, you can also suppose. Okay, its roots are given by values of lambdas. Okay, 3 values will be there. Now, just for proving it, we can use only left hand side. Okay, so here eigenvalues are given by this, where we know its roots are eigenvalues. Suppose if lambda 1, lambda 2, lambda 3 are eigenvalues, its roots are eigenvalues. So if lambda 1, lambda 2, lambda 3 are eigenvalues of A, then A minus lambda I its value will be, these are the eigenvalues. That is, this is what? Characteristic polynomial, just like this. Characteristic polynomial. So characteristic polynomial is of cubic equation in lambda. So here these three are the roots of this equation. So we can write lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3. Here minus 1 to the power 3, minus 1 to the power 3, because of lambda minus lambda. So we can write like this. Clear? It can be expressed as also how? Minus lambda cube plus lambda square, lambda 1 plus lambda 2 plus lambda 3 minus lambda square minus lambda coefficient plus constant. Okay. Then eigenvalues are, just you can write here, are zeros of this. Why 0? Same thing, na? Polynomial, polynomial, polynomial. Lambda 1, lambda 2, lambda 3 are given by are eigenvalues, then also this polynomial can be written like this. Now comparing these two, this is equation 1, this is equation 2, this is equation 2. Comparing these two, this and this. So lambda square coefficient are this, lambda square coefficient are this. Just you can multiply it. You can see here lambda square having coefficient will be like this, and constant term here, where lambda is our variable for this polynomial. So lambda 1, lambda 2, lambda 3 are constant. When just multiply, so lambda 1, lambda 2, lambda 3 are the values here, plus lambda 1, lambda 2, lambda 3, and here something, here something, here something you can write. Clear? Like this. So now comparing 1 and 2, we can see that this is equals to this. On comparing 1 and 2, we get lambda 1 plus lambda 2 plus lambda 3 equals to A11 plus A22 plus A33. So this is our result. Principal diagonal element A11, A22, A33. This. And eigenvalues lambda 1 plus lambda 2. Sum of eigenvalues is equals to the sum of elements of principal diagonal. This is the fifth property. Clear? So very important. Remember it. Because this characteristic polynomial, it's 0. Eigenvalues are zeros of this. This. It can be expressed like this. And if lambda 1, lambda 2, lambda 3 are the zeros of this, are the eigenvalues of A, then also this polynomial can be expressed like this. It can be expressed like this. Now comparing these two, lambda square coefficient. So this equal to this. This equals to this. Sum of eigenvalues is equals to the sum of elements on principal diagonal. Clear? And next property is 6. The product of eigenvalues of a matrix is equal to the determinant of the matrix. So here in this part, from this part, just see 6th property. Property 6. Property 6. What is property 6? Product of eigenvalues is equals to the determinant of the matrix. So here, if lambda 1, lambda 2, lambda 3 are the eigenvalues of the matrix A, then we can write this is equals to this. Okay, this is equals to this. Clear? Now, in this equation, suppose this is 1. If lambda equals to 0, if we put lambda equals to 0 in 1, in this, these three are the, you can write like this, let A be a square matrix of order 3. And these are eigenvalues of A. Then we can write like this. So this is equals to this. If we put lambda equals to 0 here, so 0 into I, so this, then we get here A minus 0 into I, determinant equals to, here lambda equals to 0, 0, 0, and here not lambda. So 0 plus 0 plus 0 plus lambda 1, lambda 2, lambda 3 implies determinant A is equals to lambda 1, lambda 2, lambda 3. So product of eigenvalues is equals to the determinant of matrix. Okay, this is the result. Hence proved. Property. Product of eigenvalues of a matrix is equals to the determinant of the matrix. So this is 6th property. Okay. Now property 7. If lambda is eigenvalue of a matrix, then 1 by lambda is eigenvalue of A inverse. Property 7. If lambda is eigenvalue of matrix A, then 1 by lambda is eigenvalue of A inverse. So very simple, by using the transformation, we know what? Property 7. If lambda is eigenvalue of A, then Ax, lambda x, we know. Now pre-multiplying by A inverse on both sides. Pre-multiplying, just pre-multiplying. So here A inverse A, x equals to lambda A inverse x, because lambda is constant. So we can write I, A inverse A equals to I lambda A inverse x, implies Ix into x. So A inverse x equals to 1 by lambda into x. We can write like this. A inverse x equals to 1 by lambda x. This is same as this. Here lambda is eigenvalue of A. So here 1 by lambda is eigenvalue of A inverse, which shows that 1 by lambda is eigenvalue of A inverse. Okay, so this is 7th property. Also important. 8th, if lambda is eigenvalue of an orthogonal matrix, then 1 by lambda is also its eigenvalue. Orthogonal matrix. We know orthogonal matrix means what? A dash A equals to I. Orthogonal matrix means A dash A equals to I. Clear? So here, just from this, if lambda is eigenvalue of A, then 1 by lambda is eigenvalue of A. So here 7th property. Property 7. Not 8. Now property 8. We know that property 8th. We know that if lambda is eigenvalue of A, then what we see here? This 1 by lambda is eigenvalue of A inverse. Is eigenvalue of A inverse. We know. Here, in this 8th property, here if A is orthogonal, A is orthogonal matrix. Orthogonal matrix means therefore A dash equals to A inverse. Orthogonal matrix. Here since A is orthogonal matrix, therefore A dash equals to A inverse. For orthogonal matrix we know. And also we know that eigenvalues of A and A dash are same. First property, A and A dash having same eigenvalues. So here, if lambda is a eigenvalue of A, then 1 by lambda is eigenvalue of A inverse. We know. That is 1 by lambda is eigenvalue of A dash for orthogonal matrix, because both are same. So 1 by lambda is eigenvalue of A dash. And we know that A and A dash are same, having same eigenvalue. So 1 by lambda is eigenvalue of also A. From above results, we can say that 1 by lambda is also eigen value of A. 1 by lambda is also eigen value of A, orthogonal matrix, where A is orthogonal. Clear? This is property 8. Now property 9. So here property 9, just I have already discussed about it. Property 9, that is, if lambda 1, lambda 2, lambda n are eigenvalues of A, then eigenvalues of Ka are just K multiplied first, second we can say R lambda 1 n power n. Clear? On the basis of this we can say the third property. R P lambda 1, P lambda 2, P lambda n. Very simple proof can be given for this property, because here see, lambda 1 to lambda n means n square order square matrix. So lambda I eigenvalue of lambda I is eigenvalue of matrix. Here A x I equals to lambda I x. Lambda I eigenvalue of A, so there correspond eigenvectors xi, like this. Axi equal to lambda xi. I equals to 1 to n. I equals to 1, 2 up to n. By property, by transformation, by definition. So, for proving this constant multiple, so here just multiply it by non-zero constant both side. Axi is equals to k constant xi, implies k a xi equals to k lambda I xi for all I. As lambda is eigenvalue of A, here k lambda is eigenvalue of k. So first is proved. Which shows that k lambda I are the eigenvalue of k a I equals to 1 to this first proved. Clear? Now for proving second, just multiply this by a first. Okay, this is the proof of first. Now for proof of second, so here what we have to do? Just multiply. Increase the power of a. Increase the power of a. So implies pre-multiplied by a. Axi. A lambda I xi. A square xi equals to, here we can write, see, lambda I constant a xi, and axi equals to lambda I xi. So we can write lambda I xi. So we can write like this: square xi equals to lambda I square xi. Similarly, just again multiply by a, then a cube, again multiplied with a power 4. So up to the mth term. Similarly, by multiplying, pre-multiplying by a up to mth time, so a or m xi equals to lambda I power m xi for all I. Okay. So which shows what? What shows it? Lambda I power m is the eigenvalue of a to the power m. So lambda I power m is eigenvalue of lambda I power m is eigenvalue of which? A power m for all I. Second part is proved. By using these two parts, from first and second, we can say that these are the eigenvalues of this polynomial of matrix. Okay, so this is second part. Now third part, this was the second part. Now here third part. Third part, how can you prove third part? Combining first and second, we can, here lambda b a is polynomial in lambda. Third part, here p a is a polynomial in a. So by using first and second part above, we can conclude because this is multiplication of this is a to the power m. So combining this plus plus plus, we can get polynomial. So by using 1 and 2, first and second part above this and this, we can conclude PA is a polynomial in A, so we can conclude that lambda I are eigen values of PA. P lambda 1 to lambda n I are eigen values of PA for all I. Here I is placed by 1 for finding eigen value in P lambda I. Clear? So we can conclude like this. Now property 10. If there are very important part in property 10, if capital A and P are square matrix of same order, same type, and P is invertible, then A and P inverse A are having same eigenvalues. Okay. So for having same eigenvalues, we are considering of characteristic polynomial. Okay. So we know eigenvalues are given by, for a matrix, 0 of polynomial. So here 10 we know here we have to show that what same eigenvalue na A and P inverse AP. We have to show that matrix A and P inverse AP have same eigenvalue. A is a square matrix, P is a square matrix, same type. That's why multiplication is compatible. So here P is invertible also, so P inverse exists. Now this is A, this is P inverse AP. We can get this multiplication. Both will have same eigenvalues. We have to show that this and this have same eigenvalues. For that, its characteristic polynomial and its characteristic polynomial should be same. So that is, we claim A and B will have same eigenvalues, will have same eigenvalues A and B, where B equals to P inverse A P. For we have B minus lambda I, because we want to see the characteristic polynomial of A and B. Thus B minus lambda I can be written as, B means what? P inverse A P minus lambda I. Clear? So lambda I into I we can write. Now P inverse A P minus lambda I we can write P inverse only single I, just suppose, no, double I, like this, P inverse P. Since P inverse P equals to I, P inverse P equals to I into I equals to I. So here I equals to P inverse P. Now by associativity law, here P inverse lambda I, P inverse P, we can write like this. Here by associativity, A minus lambda I we can write just common P inverse from this side, P from this side, set like this. Okay, so B minus lambda I equals to this. Now its characteristic polynomial of B minus lambda I determinant, just take determinant on both sides, here and here. Determinant equals to determinant P inverse A minus lambda I P. Here three matrices are multiplied, so it can be written how? Separately. P inverse A minus lambda I P determinant, because determinant A B C equals determinant A, determinant B, determinant C. So here A minus lambda determinant, these are the numbers, so just write it here, A minus lambda I, and P inverse is here. Also by reverse, determinant A, determinant B equals to determinant AB. So this is equals to A minus lambda I determinant of P inverse P. So this is equals to what? Determinant A minus lambda I determinant I. And we know determinant I equals to 1. So A minus lambda I determinant. So B minus lambda I determinant equals to A minus lambda. Thus we get B minus lambda I determinant equals to A minus lambda I determinant. That is characteristic polynomial of B and A are same, which implies lambda is eigen value of A and also of B. Because this is equals to 0, the lambda is eigenvalue of B. This is equals to 0, lambda is eigenvalue of A. So lambda is eigenvalue of A and B. Lambda is eigenvalue of A, which implies that lambda is eigenvalue of A and also of B. Thus, if B means what? This. Thus, hence, you can write hence A and P inverse AP. B means P inverse AP. A and P inverse AP will have same eigenvalues. Clear? So this is property 10. Now 11. If AB are two invertible matrix, then AB and BA are having have the same eigenvalues, AB and BA. So it is also very easy by using this property. This is very important property. So we can use this. 11. We know that. That's right. We know that we can use this. A and P inverse AP have same eigenvalues. Just use this for proving if AB are invertible matrix, then AB multiplication AB and BA will have same eigenvalues. So it is simple to prove because see here, we have to show that AB and BA have same eigenvalues. For this, we can write AB. Just use this property, okay? We know here, just suppose C is a matrix, C is a matrix. So C is a matrix, C, P inverse C, P have same eigenvalues. Here in place of C, just we consider for this AB can be written as I into AB, and in place of I we can write B inverse. Here AB are invertible matrix, so A inverse B inverse exists. So here B inverse B we can write AB. We can write AB equals to I into AB. In place of I we can write B inverse B. B is invertible, so B inverse exists. Now by associativity law, B inverse BA B we can write. Clear na? So and here AB equals to, just we get AB equals to, these two are same. Now its eigenvalue and eigenvalue of BA are same by using this. Using 1 and 2, using 1, we can say that in place of C, if we take BA, we can say that BA and B inverse BA B, BA and B inverse BA B, invertible matrix C C BA BA. Yeah, in place of P, B inverse B inverse. Using one, we can say that this and these have same eigen values, implies this is equals to AB, implies BA and AB have same eigenvalues. Using 2. Hence BA and AB having same eigenvalues. This is property 11. Okay. Now 12th property. If A and B are n-row square matrices, and if A is invertible, then matrices B, A inverse B and B A inverse have same eigenvalues. You can use this property also here. Here A inverse B and B A inverse have same eigenvalues. Here A B are n-row invertible matrices. Okay, square matrix and AB invertible. So A inverse B and B A inverse have same eigenvalue. So here, as the same process, we can use what? A inverse B equals to, we can write A inverse B equals to, as the same, A inverse, property number 12. Same. This is our known result. A inverse B and B A inverse. A inverse B and B A inverse. A inverse B and B A inverse having same. A is invertible. This. So A inverse B equals to, A inverse B equals to the same. As the same process you can do it. Okay. So inverse B. Here in reverse direction you have to write A inverse B and B A inverse. A inverse B equals to A inverse B into I, you can write A inverse B in place of B, because A is invertible, so A inverse exists, so we can write A inverse A in place of I. Okay, by associativity we can write it as A inverse B A inverse A. So we get A inverse B. A inverse B equals to A inverse B A inverse A. Now B A inverse taking in place of C. So we can write using one, just this. We can say that B A inverse and A inverse in place of P, B A inverse A. A inverse B A inverse this and B A inverse in place of C. P inverse in place of have same eigenvalues, implies B A inverse and in place of this is equals to this. So A inverse B. A inverse. B A inverse and A inverse B have same eigenvalues using 2. So this is property 12. Now 13. The property 13, 0 is an eigenvalue of matrix. if and only if matrix is singular. Singular matrix means determinant A equals to 0. Singular matrix means determinant A equals to 0. Okay. So here, see, if matrix is singular, then 0 is the eigenvalue of matrix if and only if matrix is singular. So here, let lambda equal to 0 is an eigenvalue of a matrix A. Then what we can write? Lambda equal to 0 is an eigenvalue of matrix A. Then just we can as eigenvalues are given by A minus lambda I determinant equals to 0 implies A minus 0I equals to 0 implies A is singular. Clear? If lambda is 0, A is singular. Now in the reverse, if A is singular, now if A is singular, then determinant A equals to 0. If A is singular, then determinant A equals to 0. Clear? And also A minus lambda I determinant equals to 0 gives eigenvalues. So this is equals to determinant A minus determinant lambda I is equals to 0. Determinant A will give 0 minus lambda determinant I is equals to 0 implies lambda equals to 0. Clear? Complete the proof. Lambda 0, then A singular eigenvalue. If A singular, then lambda eigenvalue than this. Now this can be written like this. So lambda equals to 0. So this is the proof of properties of eigenvalues. Okay. Now proof of eigenvectors are not so required, just we have to find some eigenvectors. Okay. Eigenvectors are what? Either column vector or row vector. Just we are writing generally as a column vector component. If having a vector having component x1, x2, x3, then we are writing vector as what? Like this: x1, x2, x3. This. Clear? this vector. If lambda is eigenvalue of A, lambda eigenvalue by A matrix and corresponding eigenvector x, then just we are writing Ax equals to lambda x. Eigenvalue, corresponding eigenvector this. So for finding this eigenvector, just we can write like this: A minus lambda I determinant equals to this x equals to 0. Homogeneous equation, simultaneous equation, it can be solved if it will give non-zero solution. It will give non-zero solution if its determinant is equals to 0. By taking its determinant 0, we get value of lambda. So corresponding to this lambda, this will give non-zero solution. Non-zero solution. Non-zero solution means we can get non-zero x vector. So corresponding to eigenvalue, each eigenvalue, this system will give a non-zero solution that by which we can get eigenvectors. So here, first of all, we have to find eigenvalue, and then corresponding to eigenvalue, we will find eigenvector. This is the finding eigenvalue and eigenvector of a matrix is known as eigenvalue problem. Okay, so what is eigenvalue problem? Eigenvalue problem means finding eigenvalue of a matrix and eigenvector of matrix corresponding to each eigenvalue. Characteristic equation will give eigenvalue and simultaneous homogeneous equation will give eigenvector. So here some properties of eigenvalues, vectors are also. So note down this, very important. First is what? Eigenvector of a matrix is not unique. That means if we can get a eigenvector like this 1, 0, 2, then any scalar multiple of this, because we are finding solution by using this system, homogeneous system. So homogeneous system gives infinitely many solution for non-trivial solution. For non-trivial solution, this system will give what? Non-trivial, non-zero, infinitely many non-zero solution. So if we find the value of value of x, that is a vector, eigenvector, so there may be infinitely many eigenvectors, many solutions. So if this is solution, then also its multiplication. Suppose 2x is also eigenvectors, 3x is also eigenvector, 4x is also eigenvector. That is what? 4, 0, 8. This is also eigenvector. This is eigenvector. So there are infinitely many eigenvectors. So the eigenvectors of a matrix is not unique. Secondly, property, if we get eigenvalues, suppose A is matrix and its eigenvalues lambda 1, lambda 2 and up to lambda n, nth order matrix. So we get n eigenvalues, and corresponding to this we get x1, corresponding to this we get x2, corresponding to this we get x3, can get xn. So these are the eigenvalues and eigenvectors. Eigenvalues. So if these are distinct, distinct, different. All are different. All different. They are distinct. Then this will implies set of linearly independent vectors. If all the eigenvalues are distinct, then these eigenvectors will be linearly independent vectors. Clear? And if out of this some are equal, if that is if one or more, if two or more eigenvalues are equal, then we may or may not get linearly independent vectors corresponding to these equal vectors. Suppose out of this lambda 1 equals to lambda 2 equals to lambda 3, and remaining lambda 4, lambda 5, and lambda n, they are distinct. They are equal. Now, corresponding to these three, corresponding to this linearly independent vectors, distinct corresponding to linearly independent vectors, and equal roots may or may not get linearly independent vectors. Means if equal roots, then it can be possible to find linearly independent vectors, or may not be possible. So may or may not possible to get independent vectors corresponding to these equal roots. May or may not. Okay. And if distinct, then linearly independent vectors. And next property is two eigenvectors are said to be orthogonal if two eigenvalues x1 and x2. Suppose this is eigenvectors 1, eigenvector 2. Two eigenvectors x1 and x2 are two eigenvectors. Orthogonal. x1 and x2 are orthogonal if its dash is equals to 0 matrix. Its dash means transpose. x1 dash x2 equals to 0 matrix, then we can say orthogonal matrix. And matrix may be symmetric, may be non-symmetric. If matrix are symmetric, next property, next property what? Symmetric matrix or non-symmetric. Non-symmetric matrix, for non-symmetric matrix you can decide as just I have discussed eigenvalues and vectors. If symmetric, if A is symmetric, then corresponding to equal roots, then corresponding to equal eigenvalues, corresponding to distinct eigenvalues, distinct or different. Means if A is symmetric matrix, then corresponding to distinct eigenvalues eigenvectors are orthogonal. Means eigenvalues are distinct for a symmetric matrix. For a symmetric matrix, if A is symmetric and eigenvalues are distinct, then eigenvectors will be orthogonal. Just x1, x2, then they are orthogonal. That means this is equals to 0, corresponding to lambda 1, lambda 2. If distinct, if not equal. So in case of symmetric matrix, so this is next property. Okay. And note down further some information about eigenvectors. Okay. So very important property are this. So remember that. Now I will solve some questions regarding eigenvalue problem, that is finding eigenvalues and eigenvectors. Okay. Now take questions for finding eigenvalues and eigenvectors. The first question, so find the eigenvalues and eigenvectors of matrix. So matrix may be symmetric, non-symmetric, maybe any type of matrix, triangular, etc. So here given matrix is C. Given matrix is A equals to upper triangular matrix 3 0 0 1 2 0, 3 0 0 1 2 0, 4 6 5, 4 6 5. Matrix may be of any type. Okay, so this is given matrix. Just we have to find the eigenvalues and eigenvectors. Okay, so eigenvalues are given by characteristic equation. Eigenvalues are given by characteristic equation. Given by characteristic equation of A, which is A minus this. Eigenvalues are given by characteristic equation of A, which is this is equals to 0. Now we have to find characteristic equation, that is its value, that means value of the determinant. So here A minus lambda I means just diagonal elements multiplied by lambda lambda. So here principal diagonal are subtracted by lambda. So 3 minus lambda 1 4 0 2 minus lambda 6 0 0 5 minus lambda. So this determinant can be solved very simple, because very easy, because these are 3 are 0, so we can get just like this, 3 minus lambda into 2 minus lambda into 5 minus lambda. So very simple calculation for finding characteristic equation. Just by multiplied it, you can get characteristic equation as a polynomial of third degree in lambda. But our target is what? By factorization. Here it is already factorized. So we can get the value of lambda is equals to 3 2 5. So the eigenvalues of A are, so the eigenvalues of A are 2, 3, 5. So all are distinct eigenvalues, distinct. So we can get distinct linearly independent eigenvectors corresponding to 2, 1, corresponding to 3, corresponding to, but corresponding to every eigenvalue, every eigen values you can get infinitely many eigenvectors. So take another vectors. Similarly 3 corresponding to 3, corresponding to 5, we can get. Okay, so these are the process of finding eigenvalues. Characteristic equation. This here simple calculation, but if there is also some values, then you have to solve this determinant very carefully, and you can get a cubic equation in lambda, and cubic should be solved for finding value of lambda, and that 3 values will be eigenvalues. Okay, so here distinct eigenvalues. Now this which are distinct, Okay, now corresponding to each eigen value we have to find eigen vectors. This is lambda 1, lambda 2, lambda 3. Okay, so this is lambda 1, this is lambda 2, this is lambda 3. Now we have to find x1, we have to find x2, we have to find x3. So 3 eigenvectors will be there. So just we have to find that corresponding to this. So here now corresponding to eigenvalue lambda, the eigenvectors is given by the non-zero solution of A minus lambda I x equals to 0. Corresponding to eigenvalue lambda, the eigenvector is given by non-zero solution of this system, homogeneous system of equation. Okay, so here for lambda equals to 2. Now for lambda 1 equals to 2, for lambda equals to 2, that is lambda 1. Okay, for lambda equals to 2, we get A minus 2i x equals to this. Clear? Let here third order matrix, so there will be 3 component of x. So let x, y and z are component of vector x, that is x equals to x, y, z. Okay, then the system will give. This is the process for finding characteristic roots, that is eigen values. Okay, so now one by one we have to find what 2, 3, 5, or value is 2, 3, 5. Clear? So this 2, 3, 5. Now after this step we have to find x1, x2, x3 corresponding to 2, 3 and 5. So after this line we can so we get matrix A minus 2i means what? A this 3 minus 2 1 4 0 2 minus 2 A minus 2i A minus lambda, so 2 minus 2 and 6 here 0 0 here 5 minus 2. This is this matrix, and x y z, and right hand side 0 matrix, so 0 0 0. This. Now this is system of homogeneous equation. We can get non-zero solution because we are finding lambda by taking this determinant equals to 0. So non-zero solution we have to find from here. Okay, so you can use any of the procedure, just solving system of equation by using rank method and converting to echelon form and solving. Okay, so just also here it will be easy for finding eigenvectors if we use cross multiplication method after simplifying this system. So here we can simplify this system. So this is what 1. So we can write system already. 3 minus 2 means 1. 1 4 1 4 here 0 0 6 here 0 0 3 x y z. This is 0 0 0. Okay, now we know by using this we can do it 0. Okay, but here we see that if we use rank method, then here rank is 2, because by using this we can convert it as a 0, reduces 0, so number of non-zero is 2, so one variable will be arbitrary. But for solving this system and getting eigenvectors, just we use, it will be very easy for using cross multiplication method. Here see, if we write equation, equivalent equation, so 3z equals to 0, z equals to 0, 6y equals to 0, so y equals to 0, not here not 6z, z equals to 0 also. Okay, z equals to 0, but rank is 2, so one variable arbitrary. So for getting eigenvector, just use cross multiplication method, then we can write eigenvalue very easily. So write equation from here. Okay, implies just first equation x plus y plus 4z is equals to 0. Second equation, 0 into x plus 0 into y plus 6 into z equals to 0. Two equation is this. Now this two equation can be solved. This two equation can be solved by three equation. You can write like this: 0 into y plus 3 into z. These two equations are mostly same, so just use this. Okay, equation 1, 2. First, second. So solving this two by using cross multiplication method. Solving solving 1 and 2 we get, use cross multiplication method. That means x upon y upon z upon. What we can write? X upon 0, 6 minus 0, 1, 6 minus 0, and here y upon 0 minus 6, 0 minus 6, and z upon 0 minus 0, 0 minus 0. This value suppose equals to k. Say these three are equal, so suppose say k. Now we can write here x by 6 equal y by 6 minus 6, y upon minus 6, z upon 0, and after simplification just write, okay, x by 1, y by minus 1, z by 0 equal k. Say suppose this say, so x equals to k, y equals to minus k, z equals to 0. Therefore eigen vector is x1 equals to x, y, z. You can write k minus k, 0. You can take common k, constant k, 1, minus 1, 0. 1 minus 1, 0. Okay, so 1 minus 1, 0. So here k equals to, if we put k equals to 1, 2, 3, 4 an infinite value, so we can get infinitely many eigenvectors. So it can be taken as an eigenvector corresponding to the eigenvalue lambda equals to 2. So corresponding to lambda equals to 2, this is eigenvector. So for k equals to 1, we can write only 1 minus 1, 0. So this is eigenvector. Okay. Here lambda equals to what? 2, corresponding to 2. There are infinite value if we put k equal to 1, 2, 3, 4 and so on. As a similar process, just find remaining 2 eigenvectors. Okay, solving process is this. Clear? Now for lambda equals to 3, 2 and then 3. First of all, for lambda equals to 3, we get a minus 3I x equals to 0 implies the matrix lambda in place of lambda will be 3 will be 3 will be 3. Okay, so matrix will be different. Same process will follow for finding. So here matrix will be what? 0, 1, 4, 0, minus 1, 6, 0, 0, 2. 5 minus 3, 2. So this will be the equation. Now here we can see also that by using this it can be reduced as 0 and is 10. So 0, 10, 10, 2 also can be converted to 0. Here also 0. So for solving, just use equivalent equation and by using cross multiplication method. So it can be written as 0 into x plus 1 into y plus 4z equals to 0. First equation. Second, 0 into x plus minus 1 into y plus 6z equals to 0. And last, 0 into x plus 0 into y plus 2 into z equals to 0. So this is equation 1, this is equation 2. Just take first equation and solve it by using cross multiplication method. What will be the value? X. So 6 plus 4. 6 plus 4. Now y. Y. So 0 minus 0. 0 minus 0. Z. 0 minus 0. 0 minus 0. So we get what? X by 10 equals to y by 0 equals to z by 0 implies x by 1 equals to y by 0 equals to z by 0 equals to k. Say clear? We can write like this. So from here x equals to k, y equals to 0, z equals to 0. Hence, therefore, eigenvector can be written as what? For lambda equals to 3. For lambda equals to 3, what? K 0, 0. This is eigenvector. It can be like k 0, 0, k 0, 0. So k can be taken common. Now put k equals to anything. So infinitely many eigenvectors can be taken. So for a particular k equal to 1, then 1, 0, 0 is the eigenvector corresponding to lambda equals to 3. Similarly, for lambda equals to 5, find. Okay, so here minus 2, minus 3, okay, for lambda equals to 5. Our matrix is converted like this. Now here rank is 2. So one variable arbitrary. But we are using cross multiplication method. So write equation 2x plus y plus 4z equals to 0. 0 into x minus 3y plus 6z equals to 0. So this is equation 1. This is equation 2. Now solving this. So x upon 6 plus 6 plus 12 and y 0 plus 12 and for z 6 minus 0. So we get what? By cross multiplication solving it. So x by 18, y by 12, z by 6. So dividing by 6. So 3, 2, 1 equals to k. Say. Okay. So it will give what? X equals to 3k, y equals to 2k, z equals to k. So here 3, 2, 1. 3k, 2k, k. So k can be taken common. 3, 2, 1. So 3 corresponding to lambda. So very simple, finding eigen third eigenvector corresponding to 5. So x1, x2, x3 eigenvectors corresponding to lambda equal to 2, 3, 5. We got. Okay. So here k is what? Any arbitrary number. You can put arbitrary number, you can get infinitely many eigenvectors corresponding to 5. So for a particular k equal to 1, so 3 to 1 is eigenvector. So the set of eigenvectors we can write first was what? 1 minus 1 0, 1 minus 1 0, first vector, second 1 0 0, third vector 3 2 1. This is x1, this is x2, x3. 2 3 5, lambda lambda lambda. First one to 2 3 5, x1 x2 x3. This can be taken as a eigenvectors, linearly independent eigenvectors. They are independent. Okay, so this is the process for finding eigenvalues and eigenvectors. That is solving eigenvalue problem. Okay. Now take another questions for equal, when we get equal eigenvalues. So here distinct eigenvalues, so all these are independent, linearly independent eigenvectors. Okay. So here just same process will follow for finding eigenvalues and eigenvectors. So take another questions for finding. Find all the eigenvectors, eigenvalues and vectors of the matrix here. Given matrix A is A equals to minus 2, 2 minus 3, minus 2, 2 minus 3. Just we can write matrix here. Minus 2, 2 minus 3. Minus 2, 2 minus 3. 2, 1 minus 6. So 2, 1 minus 6, and also what is given? Minus 1 minus 2 0. Minus 1 minus 2 0. So this is our given matrix. Now we have to find its. This is not upper triangular matrix. It is not symmetric matrix. Different type of matrix, non-symmetric matrix. So find eigenvalues and eigenvectors. Okay. So same process will follow. So I will write in very short. So see. Eigen values are given by a minus lambda I equals to 0. So a minus lambda I. This minus lambda I means minus 2 minus lambda, 1 minus lambda, 0 minus lambda. This diagonal elements. Now 2 minus 3 minus 6, 2 minus 1 minus 2. So this determinant is equals to 0. Now we have to solve this. Okay. By solving this determinant, we can get a cubic equation in lambda. So how? Minus 2 minus lambda, this into this, minus lambda into 1 minus lambda, minus minus plus minus 12 plus 2 into this into this 6 minus minus of minus 2 lambda. So plus 2 lambda plus minus 3 into this into minus 4 plus 1 minus lambda. Plus 1 minus lambda. This is equals to 0. Equals to 0. Clear? Now, just after simplifying it, you can get lambda q lambda square minus 21 lambda. Lambda q plus lambda square minus 21 lambda minus 21 lambda minus 45 equals to 0. Minus 45 equals to 0. Just simplify it, you can get like this. Cubic equation in lambda. Now solving this cubic equation, what is the method? Just try for getting a 0 of this polynomial. That is, put 1, whether 1 satisfied it or not, minus 1, yes or not, 2, yes or no, 3, yes or no, minus 2, minus 3, yes or no. If you can get a root, suppose we are getting root 1, then there will be a factor lambda minus 1. If we get factor minus 2, then there will be factor lambda plus 2. And just try to factorize this and getting value. Okay? So here, see, I think minus 3 is a root. Minus 3. By trial, minus 3 is a root. By trial, lambda equals to minus 3 is a root of this equation. So there will be a factor lambda plus 3. So we can write. Now this lambda plus 3, no? So lambda square, lambda plus 3, lambda cube plus 3 lambda square. So minus 3 lambda square minus 3 lambda square plus lambda square minus 2 lambda square. So minus 2 lambda square minus 21 lambda minus 40. Just try to write it in every term as factorized form. So here lambda square, lambda plus 3. Now here minus 2 lambda, lambda plus 3. So here we see that after minus 2 lambda square, this minus 6 lambda extra. So minus 6 lambda, so plus 6 lambda. So plus 6 lambda is here. So minus 15 lambda minus 45 equals to 0. Now another part, lambda plus 3 minus 2 lambda plus 3, here 15 is common, so lambda plus 3 equals to 0. So lambda plus 3 can be taken common. Okay. Lambda plus 3 taken common, we get lambda square minus 2 lambda minus 15 equals to 0. Now factorize this second minus 2 lambda, 3 and 5. We can write 3 and 5 because minus 2 minus 15. So what? 3 and 5. So here lambda plus 3, lambda minus 5 equals to 0. Now here lambda equals to minus 3, 5. So minus 3, 5. Thus, hence, eigen values are 5, minus 3. We see that repeating here, two roots are equal. So one by one, this is lambda 1, this is lambda 1, this is lambda 2, this is lambda 3. But lambda 3 are, these are equal. So now we will find eigen vector. Okay, one by one, just write and solve it. Okay. So here equal roots and matrix is not non-symmetric matrix. So linearly independent eigenvectors we can write. So first of all, corresponding to 5, for lambda equals to 5, we have system of homogeneous equation a minus 5 I x equals to 0. Same process had in the previous question. Here write matrix a minus 5I means diagonal are subtracted by 5. So minus 2 minus 5, 2 minus 3, 2, 1 minus 5, minus 6, here -1, -2, 0, -5 matrix, and this is with component x, y, z, and right hand side is 0, 0, 0. Okay, this. Now write -7, 2, -3, 2, -4, -6, -1, -2, -5. This x, y, z. Now it can be solved also by cross multiplication method. So here write its equivalent equation, and also we can convert it at 0, and by using rank method we can also solve, but cross multiplication method is simple. So here -7x plus 2y minus 3z equals to 0, 2x minus 4y minus 6z equals to 0, minus x minus 2y minus 5z equals to 0. This is equation 1. Equation 2. This is equation 3rd. So you are taking first two equations for solving. Okay. Just we have to find one by one eigen vectors. Okay. Here we are giving the process. How can you find? So solving first and second. Just use cross multiplication. So x upon minus 12 minus 12 minus 12 minus 12, and y upon minus 6 minus 42, and z upon minus 28 minus 4, 28 minus 4. So xy minus 24, y upon minus 48, z upon 24. So we can simplify it x by minus 2, y by 1 minus 1 minus 2, and z upon 1. Just you have to write as simple form. So divided by minus 24. 1 minus 1 is plus 2 minus 1. Okay. And at this stage, just write equals to k, say. Implies x equals to k, y equals to 2k, z equals to minus k. Therefore, eigenvector for lambda equals to 5, x1 equals to x, y, z equals to k, 2k minus k. So k is common, we can write 1, 2, minus 1. Okay, 1, 2, minus 1. 1, 2, minus 1. So this is eigenvector corresponding to 5. And k may be any value. So x1 equals to, we can write 1 minus 2 minus 2 for k equals to 1. Okay. So this is eigen vectors corresponding to lambda equal to 5. Similarly, minus 3 minus 3 both are equal second time. So here we can find values just see for second lambda equals to minus 3. So lambda equals to minus 3, that means here plus 3, minus minus plus 3. So minus minus plus 3 plus 3 plus 3. So here 1 4 3. Now here see 1 2 minus 3, 1 2 minus 3, 1 2 minus, all equations are same. We can make this to row 0 by using this. So also we can write like this: 1 2 minus 3 0 0 0 0 0 0 x y z equals to 0 0 0 by suitable row transformation, because add this to here 0, 2 times of this subtract from here 0, minus 6 is subtracted from minus 6 0, so 0 0 0 like this. So here we get only single equation: x plus 2y plus minus 3 z equals to 0. Single equation. A single equation. Rank 1. So number of arbitrary variable component this xyz will be 2. So x, y, any 2 can be taken as a arbitrary value. Okay. So here since three minus 2 equals to 3 minus 1, number of unknown minus rank equals to 3 minus 1 equals to 2, unknowns are arbitrary. So therefore take x equals to k1 and y equals to k2. Any 2 can be taken as arbitrary. 2 unknowns are arbitrary. So this. So from 1 we get, from here we get z equals to 1 by 3, z equals to 1 by 3 k1 plus 2 k2, k1 plus 2 k2, 1 by 3 k1 plus 2 k2. Clear? There eigenvector for lambda equals to minus 3, x2 equals to what? You can take here K1, K2, 1 by 3, K1 plus 2K2. This. Okay. Now, K1, K2, 2 arbitrary. So we can give values here. Since our matrix is what? Here, suppose matrix is non-symmetric matrix. Non-symmetric matrix, that means we can get linearly independent eigen vectors. Okay, linearly corresponding to equal roots, na? So non-symmetric matrix, non-symmetric matrix is there, so we can get linearly independent eigenvectors. So this is first was a vector, and then from here we can get two linearly independent vectors we can write, because 3 minus 3 2 times. So here, since matrix A is non-symmetric matrix, non-symmetric matrix, okay, non-symmetric matrix. So therefore, since matrix A is non-symmetric matrix, therefore we can write two linearly independent vectors as follows. Vectors for lambda equals to minus 3 as follows. We can write two linearly independent eigenvectors. Okay, as follows. How can we write? X2, x3. If K1 equals to 1, K2 equals to 0, then x2 equals to, what will be the vector? Just take 1 0, then 1 0 and 1 0, 1 0, so 1 by 3, 1 by 3. Clear? This. If we take for simplification 3 0, then so what will be the value? 3 0, then this will be 3 0 and here 1, 3 0 1. So 3 0 1. Okay. Just do that. Have to write, because there are infinitely many eigenvectors. So we have to write only two linearly independent vectors. If this. Now if K1 equals to 0 and K2 equals to 3, then x3 equals to 0, 3 and 6 here. 0, 3, 6, 2. So 0, 3, 2. 2. So for lambda equals to 3, minus 3, this is vector, this is vector. Because non-symmetric matrix. So linearly independent vector, we can write linearly independent vectors for lambda equal to minus 3 by taking arbitrary constants as 3, 0, as 0, 3. So these two are linearly independent. So x2, x3. So these are the eigenvectors. For finding, how can you find the eigenvectors with this process? Remember this process, very important process. How can you find the eigenvectors for equal roots when non-symmetric matrix is given? Now take one more questions for finding eigenvectors. Okay, here also equal roots, but for symmetric matrix. How can you get the? Because we know that for symmetric matrix, for equal roots, eigenvectors should be orthogonal for distinct eigenvectors, we know. So in this case, take matrix as given. Find all eigenvalues and eigenvectors of given matrix is A equals to, what is given? 2 minus 1, 1. 2 minus 1, 1. Minus 1, 2, minus 1. Minus 1, 2, minus 1. Minus 1, 2, minus 1. 1 minus 1, 2. 1 minus 1, 2. So see here, 1 minus 1 minus 1, 1, 1 minus 1 minus 1, 2, 2, 2, 2. That is symmetric matrix. Okay. Minus 1, 1 minus 1 and minus 1, 1 minus 1. This is given matrix. We have to find eigenvalues and eigenvectors, symmetric matrix. So here eigenvalues are given by A minus lambda I, determinant equals to 0. We know characteristic equation. So here just write determinant equals to 0. This is matrix minus lambda. So here 2 minus lambda, 2 minus lambda, 2 minus lambda. So diagonal elements subtracted by lambda. Now minus 1, 1, minus 1. Minus 1, 1, minus 1. Minus 1, 1, minus 1. This. Now solve this. We know after solving this, okay, after solving this, we can get a cubic equation. Plus, listen to this, minus 1 plus minus 1 into minus 1 plus 2 minus lambda plus 1 plus 1, this into this 1 minus 2 minus lambda. 2 minus lambda is equals to 0. So it can be simplified. Now just break this and simplify. You can get cubic equation just like lambda q minus 6 lambda square minus 6 lambda square, lambda q minus 6 lambda square plus 9 lambda minus 4 plus 9 lambda minus 4 equals to 0. Just simplify it. Simplify it. Fine. This. We have to find 3 values of lambda. This is cubic. Now solve it. Just guess it. Here 4 or 6, 10, 9, 1, 10. 1 is by trial. Lambda equals to 1 is a root of this cubic equation. So there will be a factor, what? Lambda minus 1. Okay, lambda minus 1. Now we can solve it. So we can write this lambda square, lambda minus 1, lambda cube, lambda square, lambda minus 1. So lambda cube minus lambda square. So plus lambda square. Plus lambda square means minus 5 lambda square. Minus 5 lambda square. Minus 9 lambda minus 4. Plus 9 lambda minus 4 equals to 0. Now it can be solved. Lambda square, lambda minus 1 minus 5 lambda, lambda minus 1. Here minus 5 lambda square plus 5 lambda. So minus 5 lambda. So plus 4 lambda. Minus 4 equals to 0. So lambda square, lambda minus 1 minus 5 lambda, lambda minus 1 plus 4 lambda minus 1 equals to 0. So here lambda minus 1 equals to 0. Now we can factorize second degree factor minus 5. So 1 and 4. So lambda minus 1 lambda plus okay. So lambda equals to 1, 1, 4. Lambda equals to 1, 1, 4. Two equal roots. Which are eigen values of A. Clear? Now corresponding to each eigen value, we have to find eigen vector. So same process here you can follow, but yes, matrix is symmetric matrix. So for equal roots, we have to find vectors so that vector should be orthogonal. we know there is a property for equal roots for symmetric matrix eigenvector for different eigenvectors should be orthogonal. By using this condition, we can get for eigenvectors for equal roots. Here for lambda equals to 4 now, first for 4. A minus lambda I x equals to 0 . So this is what? A minus 4I x equals to 0. So we can write matrix equation. This is matrix. 2 minus 4, 2 minus 4, 2 minus 4, 2 minus 4, and minus 1, 1, minus 1, minus 1, 1, minus 1. So this is x, y, z equals to 0, 0, 0. Clear? Now simplify it. Our procedure is for by using cross multiplication here. Now minus 2, minus 1, 1, minus 1, minus 2, minus 1, 1, minus 1, minus 2. X, y, z 0, 0, 0. Now here we can see that minus 2, minus 1, 1, 1, minus 1, 2, 1, minus 2, 2. Rank will be 3 because we cannot convert it. So we can get solution by using all equations are different. So just write equivalent equation here. Minus 2x minus y plus z equals to 0. Equation 1. Minus x minus 2y minus z equals to 0. Equation 2. Minus plus. So solve any two of this equation. So first two equation. So solving for getting eigen vector corresponding to lambda equals to 4. Solving 1 and 2, we get here x upon y upon z upon x upon x upon. So x upon 1 plus 2 and y upon minus 1 minus 1 minus 2 minus 1 minus 2. Here plus 4 minus 1 4 minus 1. So we get here x upon 3 y upon minus 3 z upon 3. So we can write x upon 1 y upon minus 1 z upon 1 equals to k. Say implies x equals to k, y equals to minus k, z equals to k. Therefore eigenvector eigenvector corresponding to lambda, eigenvector for lambda equals to 4, x1 equals to x, y, z is equals to k minus k plus k equals to k 1 minus 1 1 and equals to 1 minus 1 1 if k equals to 1, because infinitely many eigen vectors if k equal to 1 2 3 4 5 6 7. So here just k equal to take 1, then eigenvector x1 equals to 1 minus 1 1. Okay, 1 minus 1 1. This is the eigenvector corresponding to 4. And this will also satisfy here 1 plus 2 minus 2 0. So third equation also satisfied. So this can be taken as a eigenvector corresponding to lambda equals to 4. Now for equal roots, yes, matrix is symmetric. So for finding here 1i, here 1, here 1, here will be 1. So this three values will be what? 1, 1, 1. All are same. This can be added to here 0. This can be added to here, subtracted here 0, 0, 0. This add 0, 0, 0. So it can be simplified for 1. It can be simplified like this. Okay, it can be simplified what? By 1. Here see, this is added, this subtracted from here to 0, 0. This subtract added from added to this 0, 0. So we can convert it like this. Zero, 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 0, 0, 0, x, y, z. By row operation we can do like this 0, 0, 0. Single equation we will get x minus y plus z equals to 0. So equation 1, only single equation. So this is 0, 0. Rank is 1. So two variable will be unknowns will be arbitrary. So here since n minus r, that is here number of unknowns 3 minus rank 1 equals to 2 unknowns are arbitrary. 2 unknowns are arbitrary. Therefore, take x equals to k1, y equals to k2. Then from 1, then from 1 this z equals to y minus x means k2 minus k1, k2 minus k1. Therefore, eigenvalue for lambda equals to equal roots what? K1, K2, K2 minus K1 Clear? This is eigen vector. Here k1, k2, two arbitrary unknowns. Now, here some given matrix is symmetric. So first of all, write one eigenvector by giving arbitrary value to arbitrary constant from ourselves, just like if k1 equals to 1 and k2 equals to 1, then just we give arbitrary values to k1 and k2, then x2 1 1 0, be an eigenvector for lambda equals to 1. Now, since given matrix is symmetric matrix, therefore eigenvectors corresponding to different roots corresponding to different eigenvalues symmetric, given matrix is symmetric matrix, therefore eigenvectors corresponding to different eigenvalues should be orthogonal. Okay. So here we see that x2 and this is orthogonal. Okay. And now should be orthogonal. So for writing another vector for a lambda equal to 1, we are giving this value not linearly independent, so orthogonal. So that's why we are now finding the x3 for lambda equal to 1. Okay. Now, let x3, x1, x2, x3 be another eigenvector for lambda equals to 1. Then orthogonal, then x3 should be orthogonal to x1 and x2 both, that is x1 dash x3 equals to 0 and x2 dash x3 equals to 0. This is orthogonality condition. x3 is orthogonal to x1, x3 is orthogonal to x2. So, what is this? x1 dash 1 dash So 1 minus 1 1 and x3 x1 x2 x3 this equals to 0 and x2 dash this dash 1 1 0. So transpose 1 1 0 x1 x2 x3 equals to 0. Okay, so this is x1. Now this implies just multiply x1 minus x2 plus x3 equals to 0 and here x1 plus x2 plus 0 into x3 equals to 0. Now solving this 2 by cross multiplication. Solving these two equation, we get what? x1 upon x2 upon x3 upon. So here x1 upon minus 1 0 minus 1, clear, and x2, so 1 minus 0, 1 minus 0, 0 minus 1, 1 minus 0, and here 1 plus 1, 1 plus 1. So this will give what? x1 upon 1, x2 upon minus 1 1 and x3 upon 2. So minus 1 1 2, minus 1 1 2. Hence x3 equals to x1 x2 x3 minus 1 1 2. So minus 1 1 2. So this x3 is orthogonal to x1 and also x2 for lambda equals to 1. Another eigen vector as A is symmetric. Matrix. A is symmetric matrix, that's why for equal roots lambda equal to lambda equal to 1, x3 is find out by using this condition orthogonal. Okay, so this x1 x2 x1 was what? X1 is 1 minus 1 1. This is for lambda equals to 4. So lambda equals to 4, so 1 minus 1 1, this x1 x2 x3 x2 x3 for lambda equals to 1. Okay, this is the process of finding eigen values and vectors of symmetric matrix, non-symmetric matrix also. So eigenvalue problem, so finding eigenvalues and eigenvectors are known as eigenvalue problem solving. Eigenvalue problem. Solving eigenvalue problem means finding eigenvalues and eigenvectors. Now I will give some questions. Just see these questions. These questions are for your practice. Okay. So by using properties of eigenvalues and eigenvectors, you have to solve these questions. Properties can be used for finding answer of some of the questions. and also solve eigenvalue problems for the given matrix. This is for your practice. Okay, so important questions. So very important topic, eigenvalue problem. Eigenvalue problem means finding eigenvalue and eigenvectors by using these methods. Okay, so do these questions and try to do more and more questions for your practice. So solve this eigenvalue problem. Okay.